Hello, I am Datan, and in this video, I'll do a quick run-through on what I've learned on the subject ECE3211L feedbacks and control systems. Across 8 experiments, I explored how mathematical models, simulation, and design techniques come together to analyze and control dynamic systems. So, on the first 2 lab experiments, modeling, which involves modeling and simulation foundations, I learned how to connect models using MATLAB's control system toolbox. I practiced series, parallel, and feedback connections, and even built MIMO or multiple input, multiple output systems by concatenating inputs and outputs. This gave me the foundation to represent complex block diagrams mathematically. Next, through Simulink and Simscape on-ramp, I discovered how to model dynamic systems graphically. Simulink allowed me to simulate algorithms and signals, while Simscape introduced physical modeling, bridging theory with real-world components. For the third laboratory experiment, which involves transfer functions and time response, I focused then on such transfer functions, which is the mathematical link between inputs and outputs. By deriving and simulating second-order systems, I saw how damping, natural frequency, and pole shape system behavior. Using the program MATLAB, I compared manual Laplace transform solutions with automated step responses, confirming how the theories and simulation results align. Moving forward onto labs 4 and 5, which involves system stability and pole zero analysis, stability became the next big theme. I learned that the location of poles in the S-plane determines whether a system is stable, unstable, or critically stable. Through the pole zero plots and impulse responses, I saw how oscillations, decay, and growth emerge. In performance specifications, I quantified system behavior using rise time, peak time, settling time, and percent overshoot. By varying damping and frequency, I understood how design choices affect responsiveness and accuracy. So as I dive deeper into the topics of feedback and control systems, we then move on to laboratories exercises 6 and 7, which involved root locus and controller design. So, root locus analysis showed me how closed-loop poles move as gain changes. The visualizations helped me design controllers by predicting stability and performance. When specifications couldn't be met with simple proportional control, I added compensators, zeros, and poles to shift system dynamics using MATLAB's CISO tool. I experimented with different placements, seeing how compensation improves settling time and overshoot. Now, for the last experiment, which is about PID controllers, which combines the proportional, integral, and derivative actions, I compared the PI, PD, and the full PID designs, learning their own strengths and limitations. I realized that PID controllers reduce steady-state error, improve transient response, and enhance stability, but I also then understood that they don't always meet every specification, especially for different complex systems. This last experiment connected everything together, from modeling, stability, performance, and design, showing how controllers are the heart of the modern feedback systems. So to conclude, from the subject ECE3211L, it taught me how to move from mathematical models to practical simulations, from stability analysis to control designs also. Each experiment built on the last, giving me a complete picture of how engineers ensure systems are not only functional but stable, responsive, and efficient.